Welcome. This episode in our Advanced Radio Design 401 series is going to focus on radio frequency interference in buildings. And we're going to look at both commercial buildings and levels of interference that you might find in a residential house. And we're going to quantify that interference using spectrum analyzers and talk about how strong that interference is relative to, for example, the thermal noise floor, which we talked about extensively in episode 2. This slide from episode 2 shows what a radio receiver has to deal with. We have signals coming in, and presumably we have one signal we want to get, and it may be fairly weak. But as we discussed in that episode, we also have noise coming in. But this slide doesn't deal with radio frequency interference. It assumes the RFI is essentially zero. So as we said, the caveats are there's no RFI, and there's also no receiver intermod issues like those discussed in episode 1. But in the real world, that's not the case. You can probably hear all the static there in the background. That's actually due to these lights up above here, as well as the ones throughout the building. So these are emitting lots of RF. In the real world, as you can see here on this spectrum analyzer plot, the analyzer is able to receive signals down to this blue line, which we call the analyzer noise floor. It's the thermal noise floor, KTB, at the antenna, plus noise figure in the analyzer. But the spectrum we see is this, and this may look like there's a whole bunch of signals here, and there are a few poking their heads up, but most of this is radio frequency interference. So what that means is this equation doesn't tell us everything we need to know. The weakest signal we can receive may be 10, 20, or even 60 dB higher than this equation might imply. Now, if you're an amateur radio operator, you may have already encountered radio frequency interference, or you may have seen it in your professional career. This is a really good presentation put out by the Amateur Radio Relay League, and it talks about sources of the radio frequency interference, the noise. And it lists some of the so-called major players, the sources of that noise in your building, and even some of the things that people can do to try to get rid of it or mitigate it or something. And what I'm hoping to do in this video is to add to that kind of information which is already out on the web. We're going to, as I said, focus on the levels of the noise and also the frequency content. So to that end, let's talk about noise versus RFI. The word noise is used for a lot of different things. It could be used for thermal noise, but it could also be used for anything you really don't want, and that would include radio frequency interference. So we're going to be drawing a distinction between what's called additive white Gaussian noise. That's this KTB kind of noise that we talked about in episode 2. We're going to distinguish that from the radio frequency interference. And here's some plots that we took with an oscilloscope and with spectrum analyzer. So let's look at the additive white Gaussian noise first in the time domain, which means using the oscilloscope. The thermal noise or additive white Gaussian noise is what we're seeing on the scope screen right now. There's no input to the scope, so this is just what the oscilloscope can show you in terms of the weakest signals possible. And the vertical scale is on 500 microvolts per division. This is a fairly new 12-bit oscilloscope with a pretty decent front end. If it were perfect, and if there were no noise, this would be a straight flat line. It wouldn't have all these wiggles on it. Now, for looking at additive white Gaussian noise in the frequency domain, and especially at radio frequencies, we often use spectrum analyzers. So here is a tiny SA Ultra model. So this is a very good low-cost spectrum analyzer that you can buy these days for about 150 bucks. And I have it terminated with a 50 ohm load, so it's not getting any signals. And the level that we see here is about minus 128 dBm. So this is minus 130, this is minus 120. It's about minus 128 dBm. And if we use the theory that we developed in episode 2, the previous episode, we can reason that this tiny SA Ultra has a really good noise figure. It's probably about 3 dB or so. But what I want to point out here is that this noise is flat in frequency. This is not the same as the time domain display that we saw before, of course. This is what level of power you've got at any given frequency. Currently we're sweeping from, let's see, the center is 120 megahertz and the span is 1 megahertz. So at all those frequencies in that range, the noise is the same within a 30 kilohertz resolution bandwidth. So that flat spectrum is what the white term refers to here. It's white noise because it contains all frequencies. It's Gaussian noise because the levels that you hit with the noise from this time to this time to this time, it's bouncing around in signal level, and that is so-called Gaussian distributed. I'm not sure why it's called additive noise. It doesn't add on a volts basis or a amps basis. It does add on a power basis though. So anyway, additive white Gaussian noise, or AWGN, is what people talk about. Meanwhile, what about RFI? Well, it's a form of noise in the sense we don't want it, but it's different than AWGN. So here's a time domain waveform that I took with a microphone hooked up to the input of the scope. That's what this is. And I was looking at how to get the audio waveforms when I talked into or sang into the microphone, and I couldn't get them because there was so much noise. But in this episode, if you want to take a look at it, we talk about how you can just put a simple low-pass filter to get rid of most of this noise and reveal the audio waveform. So this is me saying some vowel sound. Now, with these oscilloscopes, as you no doubt know, there are math functions that you can kick in, and one of them is the fast Fourier transform. And so that'll show us a spectrum plot. And so I asked it, what's the spectrum of this? And we can see it over here in the lower right corner. I set it up for 0 to 20 megahertz with the FFT controls, and you can see that it peaks around here, which looks to be around 12 megahertz, and then it tapers off, and it tapers off at lower frequencies. But in any given small range of frequencies, it looks like noise. And so what we need to do is narrow the bandwidth up, and that's what basically the low-pass filter is doing, so that we can receive very weak signals in this case. Not receive them, but look at them. But let's move on to radio reception, which is our main topic, inside this building. And a while back, I made a fairly extensive video of that, and I'm just going to play a clip from it for now. I might put the whole thing out later as a separate video. And that's it. 25 stations in the residential environment. So now we're inside the newly constructed building, and we're going to go into one of the offices here, and we will do a test of the FM radio reception in this office. You can probably hear all the static there in the background. That's actually due to these lights up above here, as well as the ones throughout the building. So here's a demo going from 88 megahertz to 108. We'll see how many stations we get. Nothing. Almost half the dial now. Oh, there's a station. So there's one station. There was something, but... Oh, there's a station. I suppose you can listen to that. So we got two stations. So that was really bad. We can only get two stations. And normally at my house, I can get like 24. Outside this building, we get close to that. But inside the building, we are just terrible. And looking at the building, you might think that radio signals wouldn't have much trouble entering it because it's mostly glass on the outside. The walls are essentially glass. But What we found when we investigated this problem is that there's actually two issues. One is the energy efficient exterior glass attenuates signals entering or leaving the building. So the signal is reduced a lot on the way in, even though they're transparent at optical frequencies. At radio frequencies, the metal glazing or whatever it is essentially massively attenuating the signal. And as we saw in the video, the interior lights in the building are producing very high levels of radio frequency interference. Quantitatively, in this building, this is only one building, different buildings have different levels of attenuation, but I noticed this problem in many buildings going back decades, that the glass we saw attenuated by up to 30 dB. So is that terrible? Well, no, because radios generally have about 100 dB dynamic range. So we could expect to lose a bunch of weak signals, but still get plenty of signals inside the building if this was the only problem. But the RFI from the interior lighting is up to 60 dB or more above the thermal noise floor. And we can see that on the spectrum analyzer plot. Here's the thermal noise floor, and here's the RFI. This is from 0 to 1 gigahertz. So 100 megahertz is right here at this first peak. So that's why we weren't able to get more than 2 stations inside the building, at least in that particular office. These ceiling lights seem to be the worst offender. I don't know if there are other offenders because you can't really turn these things off, and they're all throughout the building, and they're all hooked up to the wiring, and those wiring is acting as antennas, and so it's just everywhere. So the take-home from this is that wireless communication links, especially at VHF in this lower range here, up to 300 megahertz, which is here, can be strongly impacted. Even at UHF, and even for cell phone signals, the RFI is still pretty intense. Remember, this is up through 1 gigahertz. So we published a paper on this in the Electromagnetic Compatibility Conference held in Ottawa, Canada in 2016. And this is some of the information in that paper if you want to look it up. But if not, then maybe just freeze the video right here and read through this stuff. This is outside the building where we just have thermal noise floor plus the spectrum analyzer noise figure issues. But inside the building, we have this mess. Okay, I blamed the RFI primarily on the lights in the ceiling in this building. And that was for 2 reasons. One is in other videos I can show where when you turn the lights off in the room, the RFI noise that you get out of the radio is significantly reduced, but not enough to really receive very many stations, maybe one more station. So it's still very strong even with the lights off in that particular room. And why is that? Well, the hall lighting still is there for safety purposes, and there's other people in the building. And remember, the wires that go to these lights travel throughout the building and the walls and stuff. So they're just radiating everywhere. So here I was looking at how much is the conducted emissions from these lights. I wasn't worried about radiated emissions because theoretically they've passed some controls there. But I'm worried about conducted emissions because they probably didn't have the same wiring that we have. And I wanted to measure it. So I came up with this little probe. It's not very fancy, but it does the trick. This is a little split ferrite thing that I would then close around the wire, as you can see here, when I'm taking measurements. And I have a piece of RG58 cable, and that goes to this winding that I just wrapped several turns around. Nothing fancy here, but it obeys the physics. This AC cable has 2 or 3 wires in it, but you can have what's called common mode currents coming out of the light and traveling down this line. So what the probe is designed to do is catch the magnetic field that wraps around this wire from those common mode currents, and through Faraday's law, induce a voltage which is then applied to the coax cable, and it runs down the coax cable and into the spectrum analyzer. And what do we see? Well, we see pretty much the same kind of spectrum that we saw with the antenna hooked up to the spectrum analyzer. So it's basically radiating from these wires in a common mode sense. And I was able to get hold of one of these lights that was being replaced and take a look at the innards of it. And inside it, there is what's called an electronic ballast. The lights are fluorescent lights, so they require very high voltage. So essentially, in this metal box, there is a switch mode power supply that generates the very high voltages needed. But the theory is that as it's doing that, it's got square waves and very sharp transients, and those produce tons of harmonics, and they escape on these wires through common mode conduction. And supposedly this thing passed the US FCC 47 Code Federal Regulations Part 18 limits for the non-consumer products. So remember, we're in a commercial building. You should not expect this kind of level in most residential things, but in a commercial building, yeah. And here's a look at some of the circuitry inside that ballast and why I think this is not really choking off any of the common mode stuff that's causing us problems. At 100 megahertz and above, these are giant capacitors, and this is a really big common mode choke. So yeah, these things are designed to pass rules that limit radiation up through 30 megahertz. But at 100 megahertz, these capacitors turn into inductors, so they don't short out high frequencies like capacitors are supposed to do. And this really big common mode choke, yeah, it chokes off the low frequencies, but at high frequencies, the windings have interwinding capacitance, and so the signals just go right through. That capacitance becomes AC coupling capacitance. So what's needed are products with better differential mode and especially common mode filtering. Of course, there are trade-offs with cost. But still, you'd think that in today's world we could improve on this. And maybe we have. This was installed in 2015, but I suspect not. And in fact, I've been back in this building just a few weeks ago to check and see if anything is better. Well, these products are still there, but no, nothing's really improved. Now, before we leave these ballast things, which are essentially switch mode power supplies, let's take a look at what we see on the oscilloscope that would give us some hints as to what's going on. I did not attempt to reverse engineer this thing. If you want to know more about switch mode power supplies and radio frequency interference from them, I'm sure there are plenty of good videos out there and research papers and textbooks that can discuss that. I just wanted to see what was happening in our building. So I'm going to play this 1 or 2 minute video for you. Now we're looking at an oscilloscope display, time domain display of the disturbance that's causing the interference. And you can see the 60 hertz main periodicity there, but then there's some very strong high frequency content which we'll zoom into in a second. Here is the method for testing, very simple. Connected a small wire to the end of the scope probe, and that's our antenna. So set that aside and we'll zoom in horizontally on what we got, and you can see it's very high frequency. I zoom in more. Now I'm on 20 microseconds per division, so the periodicity appears to be about 50 kilohertz, give or take a little bit. But there's some extra information in there, some higher frequency content as well. You can see some second harmonics of that. Let me try to turn it on sweep, capture something here. Oh, that's interesting. That is quite a bit different, very impulsy there. Not sure why it's so different now. Probably because I am zoomed in to the point where it's able to capture very short events. So zooming in on that, oh, look at those pulses. Those are very high frequency pulsing. Okay, so that's where this ridiculous radio frequency interference level is coming from in this commercial building. But let's look at what might be inside a residential home and what might be causing this elevated noise floor about 20 dB higher than thermal to be happening in the home. Homes have LED bulbs in them now. But back when I did these plots, it was 2015, so these are kind of old bulbs. I still have some like this, and some of these are still running today. So let's take a look at what we see when we measure the common mode currents leaving this light bulb. So this is a little lamp that the light bulb is in. You can see it shining down here, and that's that sensor that I built. And these are the spectrums that I got for this particular bulb, which admittedly is an older one with a big giant heat sink on it. The spectrum was terrible. This is 0 through 500 megahertz, and you can see it's absolutely awful. Of course, some other technologies are better. These plots are in the same arrangement as these bulbs, in case you're interested. And you can see some of them are quite noisy, up in the several hundred megahertz range. Other ones are more quiet, like this one. In fact, how quiet is it? Well, it is almost as quiet as the background noise. This is what I get when I turn the light off. And with the bulbs on, these plots are what I get. And you can see some of them are, kind of okay. They look almost like the background noise, but some of them are terrible. Oh, yeah. And remember, measurements. I'm not in a screen room. I'm in the building that I just showed you. So this background noise is coming from all those lights in the room, even though I'm not putting my probe around the cable from the light. There's still electromagnetic fields going past this thing, and that's, I think, what is getting picked up here and shown as background noise. And oh yeah, just because these are not any different than the background noise doesn't mean the bulbs are quiet, right? This stuff is 20, 30, 40 dB above the noise floor. So we don't know what's happening down at the lower levels, right? But we can find out using one of these beautiful tiny spectrum analyzer ultra thingies. I recommend the ultra because it has a much better noise figure than the original tiny SA units. So here I have a dipole antenna with the length set up for 100-ish megahertz, and actually it is looking at 120 megahertz. That's 120. This is 119.5, 120.5. So it's centered at 120 with a 1 megahertz span. Down at the bottom is what I see when I'm not hooked up to the antennas. So this is just the noise floor of this spectrum analyzer, which is only a few dB above thermal, it turns out, if you turn on the preamp and you turn down the attenuation. So here are the settings for these measurements. I set the reference level to minus 50 dBm, and there's a good reason for that, because even though you've got this display that has, what is about 10 divisions vertically, the spectrum analyzer might have some problems in the IF section that limit its dynamic range to something like 90 dB. Anyway, I set this to minus 50 so that I wouldn't be limited by that. The resolution bandwidth for these measurements is 30 kilohertz, but importantly, like I mentioned, the attenuation is set on 0. Now, normally you shouldn't do that because you could damage the thing, but I'm only connected to an antenna, so I'm not worried about that. This thing claims that the damage level is plus 6 dBm, and I'm not going to see any signals from the antenna at plus 6 dBm. The video bandwidth I set at 10 kilohertz, a little bit less than resolution, so that the trace here is not too noisy vertically, so it's more or less a flat Gaussian additive white noise spectrum. And I notice the little bump is no longer here in the center. That's because, remember, we're now just hooked up to a dummy load. This is without any antenna hooked up. And this is what we get. Noise floor 128, 129 dBm. But when we hook it up to the antenna, this is what we get. None of the other settings were changed. The preamp's still on. And we're seeing a noise level, which is actually the RFI, from LED bulbs in my house, I could actually see this change 5 or 10 dB depending on whether or not I had the ceiling lights on in that room. But in this particular shot, I'm seeing minus 110 dBm. So that should be compared with the 129, I'll call it 130. And so you've got about a 20 dB difference. So the RFI in my house is about 20 dB above thermal. What about outdoors? Well, let's take a look. So I went outside, this is our mailbox, and I set the antenna on the mailbox so it's pretty far away from the house, 10 meters, 15 meters, I don't know. And it's pretty far away from other people's houses, 20, 30 meters. But there's still noise. Because remember, these things radiate on the power lines. And so that's a pretty big antenna, big distributed antenna. And so what I got outside was about minus 121 dBm, which is 8-10 dB higher than the noise floor. But compared to everything else, that's not terrible. Now, what does this all mean if we try to receive weak signals? That's our goal. And here's a slide where I'm really trying to put all of that together. It's a little busy, so before we get into it, let's review. What we're trying to do in Radio Design 401 is look at advanced techniques that apply to radio receiver design. And in the first 2 episodes plus this one, we've talked about a lot of things. We have the antenna, and that's really important, as noted in episode 1, to have a good antenna. Our goal is to pick up a weak signal in the presence of noise. And in episode 2, we talked extensively about KTB noise. But in this episode, we've talked about radio frequency interference and how that can be several tens of dB higher than that background noise, making it probably more important in some situations. But then in episode 1, we also talked about interferers. So there's a lot of things that go into advanced radio receiver design, which is what Radio Design 401 is about. And this is a slide from episode 1. Actually, it goes as far back as Radio Design 101 series and some of the epilogues there. And what we were trying to do here is pick up as many stations as we could. So here are FM radio stations. These are the ones I could see with a spectrum analyzer in my home office. And these are some of the radios that I use to try to pick up those stations. If it's green, it means that that radio could receive the station. So this is the ATS-25. It's a fairly new DSP-based radio. And this is an older wideband handheld radio from Yaesu that it struggled with a lot of stations. This is the one that I showed today in the video examples. And it was pretty good, but some stations it couldn't get in my house. This is an older Radio Shack SW60. It's actually better than this one, as you can see, and that's because it has better tuned filters in it. And then finally, here's a radio that we designed and built in the Radio Design 101 series. And it initially struggled with a lot of stations, but when we added the so-called Q-enhanced front-end filter, we got pretty much all the stations, at least all the ones I could see with the spectrum analyzer in my office. But remember, spectrum analyzers have a lot of internal noise typically, and so that was limiting the ability of the spectrum analyzer to receive really weak signals itself. Here is a station at 88.1, and you can barely even see it above the spectrum analyzer's noise floor. And there are other stations down here that are below the spectrum analyzer's noise floor. In theory, there could be a station every 0.2 megahertz. So 88.1, 88.3, 88.5, 88.7, 88.9, but we could only see these stations on the spectrum analyzer. So those are the ones we concentrated on. But now let's see what we can do with the tiny SA Ultra. Here is that new amazing spectrum analyzer outside my house with this nice antenna on it. For reasons discussed in previous episodes of Radio Design 401, I also have an attenuator here. There's one in this spectrum analyzer, but I didn't want to use that. I wanted better control over it. So I have this digital step attenuator that can go from 1 to like 70 dB and 1 dB steps. I'm mainly only going to be using the 2 and 8 dB attenuators here. So with both of those buttons pressed in, I have a total of 10 dB attenuation between the antenna and the spectrum analyzer. And here's the plot. That's what we're showing in the lower right. The spectrum analyzer is sweeping from 89.3 to 91.3. It's centered at 90.3 FM, which is right here. And this is a station that we struggled to get because of intermod problems, but it doesn't look too bad here. And that's because we have the attenuator in. So I'll refer you back to the previous episodes for why that is. The other thing to note about this plot is that we can actually see stations every 200 kilohertz. The span is 2 megahertz, so each division here is 200 kilohertz. So here's a station 200 kilohertz higher, here's one higher than that, and here's one, and so forth. But just because we can see them on the spectrum analyzer doesn't mean we can receive them. Remember, we have to have a minimum signal-to-noise ratio of 10 to 15 dB. So this one we're not going to be able to get. And maybe not that one, and maybe not that one. Certainly that one, and that one. And this is the reason that we could receive a more limited number of stations when we did our initial tests. This is a slightly different spectrum span. This is going from 88 megahertz up through 98, so we're really in the other slide focused mainly in this region here. But you can't see as many stations because it's not as good a spectrum analyzer. In particular, it doesn't have a low noise amplifier in it like this one does. Here it says LNA on. So this is with the low noise amplifier on. All right, now let's see what happens when we take the attenuator out. We've got 10 dB of attenuation in here. So if we take that attenuator out, this is what we get. And it's kind of what we expect in the sense that all these signals should go up by about 10 dB. So here, this station was at about minus 112 dBm, and now it's moved up to here, which is about minus 102 dBm. So that makes sense. This station was pretty marginal in terms of our signal-to-noise ratio, but now it's pretty good. It's like 25 dB signal-to-noise ratio. So that one's receivable. So now maybe we can get this one and this one and this one and maybe that, although it looks a little weird. But the real weird stuff is like this, and to a lesser extent this. This is 90.3 that we had issues with in the original receivers. And although it's not obvious here, if you review some of the previous episodes and think about intermods, you can kind of see that this is spread a little bit. But more importantly, let's look at this one. This one is horrible. It's spread very wide, and that's because there's intermods here. So even if you could receive it, you would not get only that channel. You'd be receiving the other stations that are producing those intermods. So on the one hand, if we click in the attenuation, we can reduce the intermods. Oh, this is important. Take a look at the level of this one. This is about minus 110 dBm, but up here we're about minus 94 dBm. So it went up more than the 10 dB of attenuation. That is a clear sign that there are intermods going on. The intermods go up faster than the attenuation does. If you see signals on the spectrum analyzer that when you take out 10 dB of attenuation, they go up by 15, 20 dB, that's a sign that they were intermods and potentially not even real. And that's the case here. So attenuation is good because it gets rid of the intermods, but then it brings the signals down very close to the noise floor, and even with a good noise figure, we still probably are not going to be able to get them. And that's why in episode 1 of Radio Design 401, we were focusing on this filter design to be able to select out one signal and increase its amplitude there, but not have the strong signals produce intermods that could mess us up. So that's what we're trying to do. Oh, and where are these intermods coming from? They're coming from the fact that there's a preamp in this thing, and it's on. And so, as we detailed in the previous episodes, that can generate intermods, especially if it operates at low power. The one in this tiny SA actually burns, 100 to 200 milliwatts. So it's a high power LNA. And the mixer is a very good mixer as well. So they did a really good job designing this thing as a radio receiver, but it still has problems. And that's why I feel that our research still has enormous merit. If we can do a Q-enhanced filter that can solve those problems, even at 1/100th the power, then this is a pretty significant advancement in radio design. Okay, so that's it for this video, except the possible future video list here. What we're going to do next is drill down on the intermodulation problem and understand it in more depth. We will discuss third order intercept point, some of you may have heard of, others maybe not, and something called spurious free dynamic range. These are things that radio designers really need to know. But we want to go further than that, and so we're going to talk about trade-offs with intermod performance. Specifically, noise figure trades with intermod performance. And that's going to cause us to have to go into noise analysis and simulation and circuit design. And assuming we get through all of that, we're going to go back into the design of these Q-enhanced filters that we've been discussing. So we'll go into that in more depth and then look at self-tuning, because these are positive feedback designs and they tend to oscillate if you don't control them. So we're going to learn to control them. Okay, that's it for today's episode. I hope it was useful and I hope you'll join us in the future. Thanks. Bye.